हाँ, हेलो। First, next topic is your I have total junction and last today's presentation simulation of ticket as I told Centros ticket. That's simulation of parameters of the other parameters. Later on, each of the device is optimized device. Simulation equations that hello, voice ठीक है आसन। Hello. See, we already discussed what is the Centra's ticket simulator. Ticket means, as already we have told that ticket means technology computer aided design. And as I have told, the ticket it is very powerful. Your R&D software. By using this ticket simulator, what we can do first, we can visualize the electrical characteristics of any new device, so that we can go for the next step. We can go for the fabrication of the device. Fabrication of the devices. That means for any new technology, for cost effective as well as the time to reduce the time, we can first go for the simulation. Later on, we can go for the fabrication of the devices. And for it has the provision for you can visualize the characteristics for various oxide thickness, doping distribution, or changing the device dimension, etc. That means first we can do the optimization of the devices through the simulation. Later on, what you can do later on what you can do you can visualize after optimizing the structure, you can fabricate the devices. Okay. See, the as I told, it is a numerical simulator tool and uses standard equations based on the operations required. See, under the ticket, there will be various files will be there, but among those we need mainly two files. One is a structure file, another one is an edge device file. Structure file means HDE, Central's Device Editor. It is a graphical user interface to construct the device according to the dimension. That means for various length or the width or oxide thickness, you can make the structure using the edge device. Edge device, that means HDE. Another one is your edge device. Another tool is your edge device, and it consists of basic physics. So that means for Fermi or any your mobility model, those things you have to write, and potential or electric field, those things you can visualize by after successfully run LGS. And this ticket simulation is primarily solves the Poisson's or the continuity equation, which are coupled. See, the term coupled means what? That there is a mathematical linkage between the equation, which in simpler way means that the solution of both must be such that satisfy both the equation or the sub-equation. That means from tool perspective, the solver runs both the equation for device and the computer solution, so the solution satisfies the both. That means this whatever the our central simulation is there, it based on Mendel Poisson's or the continuity equation. Simple structure. See, next we'll discuss the difference between the experiment, simulation, and modeling. As I told, the experiment means what? The fabrication of a device. In this case, you have to follow the basic process simulation. That means, see, in this case, what you have to do? You have to follow the basic process simulation, the process constant. That means what are the process like diffusion process, those things you have to follow, and you have to analyze the result and derive the inter inferences. But the simulation means what? Computational technique to predict the behavior of the devices. In case of what simulation, as I told, you can predict the behavior of the structure under quasi-real state. This is not pure real state. This is quasi-real state, and usually this is computationally complex. And modeling means what? It uses some physics-based mathematical model to understand the device operation. But this modeling that means in case of modeling, you have to use the Poisson's equations or Laplace equation depending upon the various condition or the boundary conditions, and you can find out the or you can model the electrical characteristics of the devices. But this modeling, it is still better than your simulation in terms of complexity, in terms of your computational complexity. These are the difference between your experiment, simulation, and the modeling. See, these are the fundamental key simulation. See, when you go for structure, then what you can do, first you check the, first you draw the device geometry. That means what are the your like in your MOSFET, your channel length or channel width, then oxide thickness. Those things you have to first you draw the device geometry. Then you have to mark all the coordinates. Like you start from origin. Suppose your channel length is 20 nanometer. You have to mark this coordinate system, or your oxide thickness is 2 nanometer. Those things you have to mark before designing the structure using the HDE of the ticket center simulator. Then what you have to do, you have to sort out the material. That means what are the material you are going to use. Suppose you are going to use the silicon or metal or HFO2. Those materials you have to sort out from the your simulator. There are lots of materials are there. You can sort out those materials. Then what you have to do, you have to identify the high electric field region. That means, see, suppose in your structure, there is some region, that means like channel. Channel, you have to do more meshing so that you will get the more accurate result. That's what you have to identify the high electric field region if possible. And see, if you are going to do, you want to model the device. That means if you are going to for analytical modeling of the devices, then what you have to do for analytical modeling, you always have to use the if you are going for the analytical modeling of the device, then always use the simple physics model to validate your analytical model. That means what happens? Suppose you are using the complex model in the simulator, then it is very tough to match the simulation result with the analytical modeling. That's what is better to use the simple model in the physics of your edge device, so that you are getting better matching with the simulation result. So next is what? Next is, but if you are going for, if you are not going for your analytical modeling, then you can use the complicated model for analysis of the structure, like quantum model and those things. If you are going to use those model, then the analytical modeling it will be tedious. That means you have to go for, you have to do more job. But if you are using the simple model, that means only you are doing the simulation of the structure, then you can use the complicated model for analysis of the devices. Like this, as I told, I have total three lectures on this ticket centers, and today I will discuss the how to design the PN junction. How to design the PN junction using the ticket center simulator. See, this is one structure that we have considered. In this structure, what happened? This is we have taken the length is 300 nanometer and the width is what 50 nanometer. Length is 300 nanometer and width is 50 nanometer. And this is your p-type material. That means in this case magnetic area is hole, and this n-type material, the magnetic area is electron. And this is your width of the device is 50 nanometer. See, in the decade centers, what happened? All the dimensions are given in micrometer. Whatever the dimension you will give, that will be given in micrometer. That means, see, in this case, it is 0.05 means what? This is your 0.05 into 1000. You will get 50. It is in micrometer. If you convert in nanometer, that means you have to multiply by 50. That means the width of this PN junction is a what? PN diode is of 50 nanometer, and the length of this PN junction material is 300 nanometer. And the p-type material length is 150 nanometer. The n-type material length is your similarly 0.15 to 0.3. That means your 150 nanometer. And accordingly, one thing also you note down in the while you going for the ticket center simulator design. See, in this case, your normally what happen, the y-axis positive is in your means vertical direction. If you go in the vertical direction, the y-axis will be positive. But in this case, if you go downward, then at that time your y-axis will be positive. And at the right hand side, of course, your x-axis will be positive. Similarly, if you go left hand side, x-axis will be negative. But in case of y-axis, it will be positive only if you go downward. But if you go upward, you will get the negative value of the y. Suppose you need -1 nanometer, then you have to go upward of the origin. Suppose you need the positive 3 nanometer, then you have to go to the downward of your origin. That means at the vertical downward it is positive y-axis, and vertical upward that is your negative y-axis. That is the means simulator for the ticket simulator. This is the convention given in the simulator. So like this, what you have to do to start the simulator? First you have to write SWB. I will show it how to.
Rajesh sir, please share your screen.
Yes, I go coverage of the ticket centers.
Can you share your screen? Hello, Rajesh sir. Hello, 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 Rajesh sir. Hello, hello,
Hello.
Rajesh, you are audible, Rajesh. Please continue. Continue with your presentation. Yes.
See, as I told, today we to the structure means simulation of the ticket centers using the PN junction. So today we'll discuss the theoretical part only. Okay. In the next class, I will show the demo. See, this is suppose you are going to design the PN junction, and as you have this is your PN junction for simulation purpose of the PN junction, and as you have considered length is your 300 nanometer and width is your 50 nanometer, and this is the type metal consider 150 nanometer. Similarly, entire allows to junction you have simulator always you have to use the Linux software. Click on the your desktop window, then you will get one terminal. In that one, you have to write the terminal, and in that one you have to write SWP, or sometimes you have to write only SWP, or sometimes you have to write SWP with space ampersand to open the software. That means to use the work ticket simulator. After that, this window will appear on your screen. That means this is the workbench in which you can design the structure as well as you can visualize the electrical characteristics of the any means device. Suppose see after workbench window, under this one you can design the structure as well as you can visualize the your electrical characteristics of any device. See here it is mentioned no tool. That means in this case tool is added. That means, as I told, for a device you have to use the HDE and use the device added. Those things are not added means in such. And this is the workbench for your ticket simulator. See, after that, what you have to do? After means after this window will appear, as I told, this window will appear. Then what you have to do? You have to create the project. You have to create the project. Under this create project, what you have to do the project, then new project, new project, new and new project. Then you can a empty project shell will be created, and you can give some name of this project like any name you can give like PN Junction, and then you can give the
नक्कल करके नंबर ले
name. tool and add, then you have to add the tool. That means, see, in this case, it is written that no tool. If you right click on this, you can add the tool and
लास्ट तक तो लो मेरी टाइम नहीं मिला बड़ा 20-25 मिनट
and from this one add centralized device
रियल टाइम दिया कर मतलब कितनी बार कर दिया
there SD symbol also will be there.
Bharat sir, please mute your mic. Bharat sir.
SD symbol also, similarly there will be edge device symbol also will be there. You can visualize lots of symbol, but among those you have to use only HDE and edge device, and it will appear as your square shape. And accordingly you will get the SD file in your workbench of the ticket simulator. Next, what you have to do, you have to construct the device. See, for this you have to go to the extension toolbar on the top window. See, as I told, this is the window. You can extension, and under this you run central editor. Editor. Under this extension, a window will appear of blue color. It will appear on your screen. Next, what you can do, after that you can design the structure. See, you have to only draw the device using this graphical user interface. Draw the structure like simple, like whatever you draw, means in your pen and paper, what you used to draw, the similar thing you have to draw in this blue color window. See, in this case, what you have to do, on the second toolbar, from the, as I told, after this one window here, and from the second toolbar, you have to select the material. Suppose you are going to use the silicon, that means what? You have to use the silicon as the material. That means what? You have to use silicon as the material. See, in that one, another means symbol is there. At the inside you can see this symbol, and the name of the symbol is extract coordinate. Always you have to click on that coordinate to means so that you can draw the structure using the coordinate system. That's what you have to click on that extract coordinate one symbol at the right hand side of the window. Next, you have to use the 2D tool. See, for using the 2D tool, what you can do, as I told, for using the 2D tool, see, there will be some option. There will be some option like you can draw this 2D structure, 3D structure. As your PN junction is a 2D structure, then you have to select the 2D and you have to draw the rectangle region. Because this all are your rectangle. For 3D, you have to use the cubic region. And accordingly, if you means using the mouse, you can draw the structure and in the graphical user interface. And in that one, you have to give your device dimension. Whatever the dimensions, as I told, you have to give in micrometer. You have to give the in micrometer. Suppose in this case, it is given the length is 300 nanometer and depth is 50 nanometer. That is what you can do. As I told, that is we start from 0, 0, then another dimension the doping concentration. See, if you give the one coordinate 0, 0, another one if you give 0.3 and 0.05, then you will get width of the device will be 50 nanometer and length of the device will be 300 nanometer. Like this, for this, as I told, the coordinate systems, you can use the any coordinate means according to your wish. You always, as I we have considered, the length is 300 and depth is 50 nanometer. You can consider the according to your coordinate systems, or you have to take 300 nanometer length and depth 50 nanometer. Already this point is highlighted that your positive wire systems is down. Positive y-axis, always you have to go to the downward in case of your ticket centers. You can remove the silicon box also, and you can visualize whether it is created accordingly or not. See, next what you have to do, you have to give the contact. Contact, as we know, always for any your like your MOSFET for metal or the source or the drain, you have to give the contact. Similarly, in this case also, you have to give the contact, like anode or the cathode. In case of PN junction, you have to for proper biasing of the your PN junction, you have to apply the bias. When you apply the bias, then you have to give the anode and the cathode. That's what you have to give the contact. For this one, what you have to do, you have to click on the contact. You see, this contact also you will get from the this window. This window, this that blue color window, from that one you will get the contact, and from that contact you have to select the window will appear. This window will appear. And under this window there will be, see, this is H color. H color means what? There like this, there are 8 combination of color, like 0, 0, 0, 0, 0, 0, 1, like this up to 1, 1, 1. And these are the H thickness. Like thickness you can give 4 or 3, whatever. And these are the sometimes you got vertical like this. Sometimes you may get horizontal like this. There are 6 for contact. Suppose you are using one pattern for anode, another pattern you can use for the cathode. And H color also you can use the different color. Is your red color, you can use the orange color for, like, suppose your 0, 1, 1. Accordingly, you have to change the H color also for various contact, like your anode and the cathode. And you have to click on the contact set. Once click, the contact anode will be appeared. This anode, this will be appeared. And finally, what you have to do, you have to select this. You have to activate this. You have to select this and activate it so that you can use for your for contact purpose this anode and the cathode of the PN junction. So these are the contact of your, like in your MOSFET. You have to give the contact source gate like this, or you can give, in case of MOSFET, you can give for the body also. But in this case, you need the anode and the, like this here. Each channel. In this case, we have to discuss for anode. You have to go to power source drain, and then you have all under the contact set. Like in this case, anode and the cathode. Then you can close the contact. Next, what you can do to place the contact. See, at the top, as I told, one blue color window will appear. In that, under in that one structure PN junction, as you have created already, as we have discussed already. Then in that one, you have to place the contact. That means you have to define the position of the contact. Suppose this is as we have considered, this is the structure. Suppose you have to give the contact. As you define anode the cathode, then what you can do, you have to give the position of the contact as well. You have to give the position of the contact also. Suppose in this case, you can define the position of the contact. Normally, the contacts are defined at the middle of any Suppose this is your position of the contact. In this case, the contact position will be what? It will be simply 0, and suppose that the middle will be what? Point. Here it will be point, x coordinate will be 0.3, and y coordinate will be what? 0.05. Like this. This case, you have to take your cursor, your mouse cursor to the edge of the device. Like for anode, you can go to the one edge of the device and click there. Then automatically a color, and you can right click there and click on the contact and select you wish to place the contact. In this case, either your anode or the cathode. And you say for up to this is your structure. Only see now till now we have not defined the p-type and the n-type material. Only we have taken one silicon box. Only you have taken the silicon rectangular region. Then what we did? Only we define the contact to this. Next is what we have to define the doping concentration. That means you have to create the p-type and the n-type material. For this one, you have to go to the again toolbar for the color window, and what you have to do, you have to click on the mesh. There will be one option will be there mesh, and under that mesh one option will be there define REL oblique eval oblique your EVL window, and from that one again you have to select the rectangle. See in this case you can see and only p-type at the entire material. Suppose this is a p-type material, the length is 150 for p-type and width is 50. Similarly for n-type also 150 and 50 nanometer. And what we can do? Next we are going to define the p-type and the n-type material. Then you have to go to the mesh. Then this in that one you have to select the similar to creating vision. What is drag the mouse and give the what you can do, you can a window will appear and you can define the coordinate like for p type from one you can do that material also which you can define from 0.15 to 0.03 and 0.05. This is your means for to define the doping region. One is one p-type material of with 50. Similarly, we create for n-type material also. And next, you can save the structure. Finally, what you can do, you have to define the doping concentration on this p-type and the n-type material. For this, what you have to do, you have to go to the device at the top of the window. At the top of the blue color window, one option will be there, device. At the top of the window, you have to click on that device bottom. Then what you have to do, you have to click on the you have to define your constant doping profile. A box will appear, as a result, a box will appear, and under that box, what you have to do, by default, this name will be appear. You can use this for your p-type region. This is for your p-type region. And under this one, you can define the boron, your doping concentration as well as the doping type. As we know, p-type means what? It is p-type. P-type means group 3 semiconductor dope. That means you can select boron. And you can define, you can give the doping concentration value is 1 in 90. And you have to click on the add placement. Okay. Those options will appear. This is for your p-type material. Like this, it will appear. As you can see, this is your window 1. You can give the constant doping profile. And this is a boron type doping. And the concentration will be 1 in 90. Similarly, repeat the steps for your window 2 also. And this is your n-type material. You can define n-type material. And in case of n-type material, in place of silicon, boron, you can give arsenic as the your dope. You can use the arsenic as the doping material for the n-type material, because you know if you have to use the group 5. Okay, and you can give the doping concentration like this one. Next, what you have to do? Always you have to define the mesh. Mesh means what? You have to suppose, as I told, the ticket is based on the Poisson's and the continuity equation. That means what? Because as it is based on Poisson's and the continuity equation, that means you have to define some region in the structure so that it will solve the equation. The software automatically it will solve the equation, but you have to give the finite mesh so that you will get the accurate result. See, these are the under that one. you have to give the maximum mesh size and the minimum mesh size. Normally, these are the standard size. In this case, maximum mesh size we have given 3 nanometer and minimum mesh size we have given 1 nanometer for both X as well as the Y dimension. That means for this 2D structure, we can give this 3 nanometer maximum mesh size both X and and the Y. Similarly, for your 1 nanometer, you can give the minimum mesh size for both X and the Y. After that, you can view the mesh. For that one, again you have to go to the mesh and you have to build the mesh. And a structure window will appear, and you can visualize the structure with the mesh. Okay. So next, this is the structure finished. And next, what you have to do, you have to copy the means. See, when you creating the structure, under that blue color window, as I told, will appear. Under that one, ports also will be automatically generated. Whatever you are doing, whatever you are defining the mesh or doping concentration or the contact, all those things will be generated. Means the code command will be generated under that your blue color window. That means that GUI window it will appear. Next, then we have to copy this code and you have to paste in the SDE, because SDE is used for your structure. See, in this case, then what you can do, as I told, it's you have to copy the all the command. You can see that by using the Control A, and you can copy the command by using Control C. But do not close the window. Just you have to minimize whatever the blue color window. Just you have to minimize the window. Then once you minimize this one, there you can see the centrus workbench window. Then in this one, as I told, this no tool, if you click on that one, you will get some tool, add tool, then you will get some tool like SD and the SD files. In this SD, under this workbench file you have opened already, added the SDE, then you have to right click on the SDE, and if you right click on the SDE, you can see there is some option edit command, and from the edit input, from that one you have to select the command, then automatically will appear. In that one you have to paste the command and you have to set the command. See, whatever the command you are getting from your structure, that means by creating the structure, that you have to copy in the SD. But there is some other means you can modify the structure also, because there is some symbol, those are not necessary. You see, for better visualization of the or for better visualization or for better understanding the code, you can remove this command. There is some symbol or this first bracket, those symbol you can delete from the command. Similarly, the all command which represents the save action performed during GUI uses, they shall appear with this command like this. Whatever the command like this, you can delete those command also for better understanding or for better your visualization of the command. Similarly, you can delete this command also, body 50. Similarly, there will be some command like this, your this inverted comma or inverted anode. Those command also you can delete from the from the SD file. Like this, there will be some command representing any undo action performed during your graphical user interface use. Similarly, you can change the command. See, whatever this is the file of your this is the location of your software. This is the location of the software. Okay, like this, it may vary for system to system or user to user. Like here, it is here. See, whatever we are doing, it is under 10, and we have our project name we have given as PN, and our project under this project name we have created a structure we have given name as PN. This is the tab. This up to this it is the location of your software. Up to this it is the location of your software where you have uploaded the software. and this is the temp file. This is the temp file. Under this only you have to create the project. We have to create the project name is PN, and under this we have given the name of one file as PN2. Then you have only what you have to do. See, one command will be appear like this, and under that one you have to write SC box method. Under your inverted comma, you have to write your PN2. You have to write PN2. Okay. See, next, this is the your up to this. This is your modifying the command. Next, you have to verify the file. For verify the file, what you have to do? Again, you have to go to the your CentOS workbench where we have already added the SD. Then what you can do? You can right click on the SD and run the. There will be some option run. You can run the your SD file. After that, you can when you run the SD file, automatically the structure will appear, and you can save the structure. Or if there is some error also, it will show the error. If there is some error in the command, it will show the error in which line there is the error. Okay. See, in the structure there is in the work. Actually, here it will appear. It is not visible here. Here it will appear your like your yellow color or red color, blue color or violet color like that. If yellow color means it is successful. Red color means this. Red color, then that means there is some problem in the command. Like this, if it is yellow color, that means your structure is created successfully. And as I told, on structure editor will appear. You can save the structure and can name as you have given the structure name as PN. Similarly, see whatever we did, this is your structure part. As I told, next what you have to do, you have to visualize the result. That means how you can, this is the structure. After creating the structure, you have to visualize the result also. That means you have to use some model, physics-based model you have to use. And in that regard, what you can do, you can add the edge device in the simulator. See, for edge device, what you have to do, again, you have to go to the CentOS workbench and click on the node tool, click on the tool and select the symbol. It will be mentioned in your, when you click on that tool, edge device symbol will be automatically, and you have to select that symbol and click on the OK. See, this is your, next we'll discuss the command for edge device. Structure, this is the command for edge device. Under the edge device, you have to define this command. See, these are the file. File means there will be some input file also, there will be output file also. See, this is the, you have to call the structure. Whatever structure you have created using the SD, that structure you have to call in this edge device file. Like we have given the name as what? Your PN2, that's what you have to call the structure as PN. And this is the extension, your underscore, this is the .tdr, this is the extension of your, and this is the parameter means what? We have used the silicon as the material. That means silicon also, it has some material characteristics like your band gap or doping concentration or some mobility parameter. That's what we have called the parameter file in this, under this input section. And these are the output file. Under this output, you can give any name. You can give any name, but it's better to give the same name as your input file name, so that you can easily understand that this is the output for this file on. You can give any name. You can give 1, 2, 3 also. You can give your name also, but there will be no impact on the result. But it's better to keep the same name so that you can understand this is the output file for this structure on. Avoid any confusion in the while handling the multiple file lecture. See, next is what? This is the electrode. Electrode, as I told, you are going to use the anode in the PN junction. We have defined this is the voltage. One is -1, cathode we have given 0 volt. This is the initialization of the voltages, defining the bias condition. And these are the physics file. Physics file means what? This will cover the physics and means you can, all these things are also mandatory. the your user manual of your ticket centers. See, Fermi means it will, as I told, we are going to use the Fermi type distribution, and this is your effective your for energy band gap narrowing model. You have to use the slot book model, and this is your doping dependence mobility model you have to use, because as I told, in case of your silicon, it has some mobility parameter also. That's what we have used the, or to study the characteristics, mobility characteristics of the charge carrier, you can use the doping dependence mobility model. And this is the recombination or generation model, band-to-band generation, and SRS recombination, Shockley-Hill, the SRS recombination model you have to use for this is injection structure. See, this is the part. Plot means what you are going to visualize. Like if you are going to visualize the electron density or hole density, you can visualize. And similarly, the current, total current or electron current or hole current, you can visualize. Similarly, you can visualize the your electron mobility, hole mobility, or you can visualize the potential or electrostatic potential. Similarly, your recombination generation also you can visualize, avalanche breakdown, avalanche generation, like this is the band gap or conduction band, valence band, energy band gap. All those things you can visualize, and this is the your plot section, and you have to define whatever you want to means extract from this structure or from the corresponding structure. You have to write under the plot section. And this is your math part. Math part means yeah, whatever is there, always is better to recommended to remain untouched. This is the last step, and this is for error and debugging if needed. This is for only checking the error and debugging if needed. And this is the final bias condition you have to define. As I told, yeah, these are the iteration method, the Poisson's or couple Poisson's equation. And see, in this case, you have given the anode voltage only 1 volt. Okay, that means what we are changing the anode voltage from -1 to the +1 volt. See, this is the range of the voltage. We are changing the anode voltage from -1 to the +1 volt. Okay, this is the final step. So after that, what you have to do, you have to like your SD, the similar steps you have to follow in case of your SD device. You have to right click on the SD device, and there will be some options for your run the program, and you can run the program. And if it is successful, it will appear as yellow color. If it is means fail the program, then it will appear as red color. Then now the last step is what? You have to visualize the result, because you have to visualize the result, whether you are getting the forward bias or the reverse bias characteristics for silicon diode properly or not. For that, there is two files. One is your .tdr file, another one is your .plt file. See, under this means you have to use both the file, but there is some difference for both this file. See, for visualize the result, you have to go to the extension and run central visual. You can see this is the extension. Under this extension, there is one option will appear, central visual. That is for visualization of the result. You can visual. Under that one, you can see two files. One is with extension .tdr, another extension is a .plt. You can use this .plt file to visualize the current, like your in this case diode current versus your diode voltage. To visualize, you can use this .plt file. Like in case of MOSFET, to visualize the drain current versus your drain voltage, or you can drain current versus your gate voltage. You can use this .plt extension to visualize the current, or by using this .plt you can extract you can form the current, like in your MOSFET you can extract the on current, off current, etc. Similarly, .tdr file, .tdr to visualize the .tdr file, from the .tdr what you will get the various parameter like your mobility. You can visualize the mobility, energy band gap, energy band gap, or the mobility, etc. like this. These are the dot detail and the LT. Okay, see up to this, whatever the I discussed, this is a basic introduction of the ticket tool simulator, and we have only shown the PN junction, how to design the PN junction. Okay, how to design the PN junction using the ticket central simulator. Like this, there is we can design the MOSFET or the tunnel FET, etc. In the consecutive class, I will show this how to design this PN junction. I will show this the next class or next lecture. Similarly, we'll highlight it also. I will highlight also how to design the MOSFET or the tunnel FET by using the ticket central simulator, and how to extract the result, or how to visualize the result, or how you can plot the various characteristics like energy band gap or your band-to-band generation, drain current, etc. Or and final point is what you have to extract the result from the simulator. That is also one of the main important point. That one also will show in the in the coming class. Okay, thank you. Thank you. Any question anyone want to ask? You can ask the question.
So thank you very much. So we are signing off today's session. Tomorrow we'll meet again at 2 o'clock. Okay. So see you tomorrow 2 o'clock.